Okay. Okay, we'll start the next session, which is about advanced cryptographic primitives, to distinguish it from primitive cryptographic primitives. The first talk is by Mariana Raikova on advanced cryptography on the way to practice.
Thank you. Good morning. So today I'm going to advocate that it's time that some of the advanced cryptographic techniques that we have been developing also be put on the map of practical cryptography. So, and the first question, of course, is what is the definition of advanced cryptography? For the purposes of my talk, this would be any primitives and techniques that look beyond the security of data at rest and communication channels. And for this, we have been using techniques such as encryption and digital signatures. So we will be interested in other types of techniques from cryptography, more specifically techniques that are looking at the protection of computation on sensitive inputs. So the type of functionalities that we will be interested will be giving us the ability to have multiple participants that have private inputs, and we would like to be able to compute some specific functionalities on their inputs while protecting the privacy of these inputs. And of course, we would like to be able to achieve this without having this magic hat, but rather any trusted party in the system. And in these talks, I will touch on three types of such advanced cryptographic primitives, which include multi-party computation, differential privacy, and zero-knowledge proofs. So when I think about the development of cryptographic research, it has constantly been introducing new techniques and new functionalities, but at the same time, the adoption and practice has been limited to, for a long time, on very narrow part of these cryptographic primitives, and more specifically focused on these data protection primitives. Only in the last couple of years, we have seen companies, both big companies and small startups, starting to tap into these more advanced cryptographic primitives. And I'm hopeful that in the future, we will increase the rate of adoption of these much more powerful cryptographic techniques. And in this talk, I will overview for you some of the development in these three areas that kind of give me this hope. And I should also first tell you that my inspiration for this talk came by listening to the invited talk of Shai Halevi at CCS this year, where he made the statement that advanced cryptography is needed, fast enough to be useful, and also not generally usable yet. So in this talk, I will give you my perspective on this question, and I would like to start by saying that when we think about efficiency, this should always be coupled with utility. And they're often not universal measures for efficiency. It's always good to be fast, but sometimes communication is the limiting factor because this is a shared resource, bandwidth is shared resource, and we have to compete for it. In different settings, we might have incentive to do some pre-computation, and sometimes the participants in our protocols have different asymmetric resources that we have to be careful about. And also, there are many settings where we can really make meaningful trade-offs between efficiency and utility. And also, some of the examples that I'll be talking about in this talk will be inspired from what I saw in a privacy-preserving machine learning workshop that we organized with NeurIPS in December. So let me start with the need for advanced cryptography. I think we all agree that nowadays data is one of the most valuable resources. We like to gather a lot of data and analyze it. We like to build machine learning models and then use them to predict and target. And one of the properties is that oftentimes the value comes in settings where we are putting together private data sets that are coming from multiple sources. So this inevitably brings challenges when it comes to data use. Having private data is inherently a liability. You have to be careful about internal and external adversaries, about being subpoenaed for your data. There are many regulations that also restrict the use of private data and sharing of private data. And if you're not careful with your algorithms, they also might become source of discrimination. So in this context, privacy-preserving computation brings the promise that we can get utility without sacrificing the privacy of our data. So we can reduce liability, we can enable new services for analysis that were not possible before. and we can also have better user protection. So in my talk, I will focus on two scenarios and give you techniques that have been developed for two scenarios that I think are indicative for many of the practical applications where we are thinking about privacy-preserving computation. The first scenario considers several computationally powerful participants that are connected and available to participate in our protocols. And this models settings where we have several companies, for example, that are interacting and wanting to compute something that depends on their distributed resources. The second scenario is named federated learning and considers the setting where we have one powerful computation party, and then we have many weak devices that can talk only to this one computational parties, and these devices have limited resources and also may drop out during the execution of our protocols. So let's start first with the first scenario and look at some techniques that have been developed in cryptography to facilitate privacy-preserving computation in this setting. And the first example that I will give you is the functionality of private set intersection, which asks the question, if we have two input parties that have two input sets, how can we compute the intersection of these sets without revealing anything more about the inputs? So this simple functionality has been useful in many settings where we have, for example, two hospitals that want to find their common patients, or we have the list of terrorists and then a list of passengers on a flight, and we want to find the intersection. And this problem has been widely studied in cryptography. We have had many solutions developed, and here I want to show you the efficiency of the currently most advanced techniques. And here in this setting, we consider two adversarial models. In one of them, the weaker one is called semi-honest, where you assume that parties behave as prescribed by the protocol, and the other one is malicious, that allows the participants to arbitrarily deviate from your protocol. So the current state of the art tells us that we can achieve private set intersection for sets of over 1 million elements, in the semi-honest case in under 10 seconds, and in the malicious case in about an hour. So one application of a related problem called private intersection sum is also used by Google for aggregate attribution. Another example that I would like to discuss is called private information retrieval, where we have one server that has a database, and then we want to enable a client to retrieve one record from this database without revealing what exactly is being retrieved, because maybe the selected record depends on some private information, some health information, or some preferences that we want to hide from the server. The solutions for this problem leverage a powerful cryptographic primitive, which is called homomorphic encryption, and which allows us to compute on encrypted data. And I chose to show you this example because this showcases the current efficiency of homomorphic encryption techniques. And what we are able to do today is we were able to run private information retrieval on databases of size over 4 million, where the data items are of size 288 bytes, in about 12 seconds. So this shows the immense advancement in the techniques for homomorphic encryption as well. And certainly, we would like to also look at the question of general two-party computation that allows us to compute any function that depends on the inputs of two parties without revealing anything more about their inputs. And there has been a tremendous amount of works that have developed general computation frameworks. And oftentimes, the functionality that's used to benchmark such implementation is secure computation for AES, where one party has the key, one party has the input. And I have selected here a few representative works. There are many, many more, just to demonstrate the improvement in efficiency in these protocols over the past 20 years. So we have seen multiple orders of magnitude improvement in the computation time, starting in the beginning with needing hours in the semi-honest case and more than a day in the malicious case. And nowadays, we can run secure AES in the semi-honest case under 1 millisecond, and in the malicious, we need about 6.6 milliseconds. So that's another very impressive development in general secure computation. And as I promised to you, some of the examples that I want to cover here are coming from privacy-preserving machine learning, which is another area that I think is a very high use of such techniques. And here I want to start with the statement that if you want to get the most efficient approaches for privacy-preserving machine learning, probably out-of-the-box use of secure computation techniques is not the right approach. Oftentimes, we need to make the machine learning algorithms MPC-friendly. And what do I mean by this? For example, most machine learning algorithms are expecting to use floating point computation. And when it comes to secure computation, this is very, very expensive. So many approaches have been trying to redesign these algorithms to be able to work with fixed point arithmetic. Also, some nonlinear functionalities that come from ML are very expensive in secure computation, so people have been coming up with efficient approximations, such as approximation for the ReLU function. Also, we can go from the other direction, where we'll be optimizing secure computation techniques for machine learning algorithms. In particular, we can come up with specialized primitives that are targeted at widely used functionalities, such as matrix computation in machine learning, or we can build MPC protocols that exploit the fact that we'll be interested only in approximate computation. And we have some examples, for example, approximate FHE constructions. Also, machine learning is the place where we can really trade off between accuracy and efficiency, especially regression type of algorithms that have this iterative nature, where we can really choose what level of accuracy we need and what price and efficiency we want to pay. So, and one last point is that sparsity is really matters in machine learning, and there have been developed a lot of computational approaches that, for example, are specified in the sparse BLAST standard interface that aim to leverage sparsity. And we can try to translate this also in the machine learning, in secure computation techniques. So let's look at some examples from what has been done in this area. And the first example is privacy-preserving computation for distributed linear regression. So the setting here is that we have a database, and this database is vertically partitioned between multiple parties, and the goal is to compute a linear model using secure computation on this data. So in a work with several co-authors, we looked at this question, and the main technique that we use to compute these linear models is solving a system of linear equations. So we considered multiple ways to solve these systems of linear equation in secure computation, and we found out that an approach based on conjugate gradient descent that allows us to really trade off accuracy and efficiency seemed to be the best performant. And for this purpose, we also needed to come up with a variant of this algorithm that works well with fixed point arithmetic. So what we observed is that if we run CGD only for 20 iterations, which means that we don't have to go to convergence of this algorithm, we already get the error that we also get from exact solutions. And this also allows us to improve on the efficiency compared with the computation of the exact solution in secure computation, and we can run this in a couple of hundreds of seconds. Just as a reference point, running the whole computation of the learning the linear regression model on 500,000 records, depending on the number of attributes, from 20 attributes, it takes about 15 seconds, and going to 500 attributes, it takes about 2 hours to compute the ML model. And of course, when we talk about ML, we have to look at neural networks. So here is an example where we have two parties. One of the parties has a convolution neural network model, and the other party has an input that needs to be classified according to the model in a secure manner. So here I will give you an example from a work from Usenix this year that proposed a hybrid approach between fully homomorphic encryption and garbled circuits. And they evaluated their solution on the MNIST dataset that contains images, and the goal is to classify this image as a particular digit. So they explored several CNN topologies, and all of their solutions ended up running in less than a second. And their major distinguishing factor was how much communication they needed, which depended on how much garbled circuits versus FHE the approach was using. And as I mentioned, sparsity is often very important in machine learning. So that's why we developed a framework that proposes secure computation techniques that leverage sparsity for machine learning algorithms. And we try to emulate the components of general architectures for scientific computing, which propose different layers of abstractions, starting from a layer that's accessing memory, going to a layer that does linear algebra, and then the application layers that build on top of it. So we developed all of these primitives targeted for use of sparse data and proposing this layered architecture on which you can kind of obliviously implement applications on top of them. So just for purposes of comparison, we run computation of logistic regression training using sparse data, and we compare it with the state of the art, which is the secure ML paper from Security and Privacy 2017. And we showed that by leveraging sparsity in the input data, we can achieve 2 to 5 times improvement on the times for running this secure computation, depending on the input sparsity. So next, let's move to the other scenario that I described to you, which is federated learning, where we have this stark communication with one powerful and then weak devices. So in this setting, one application scenario is secure aggregation, where the goal is to have each of the devices yes, don't make me scared. So the goal here is to have each of the devices compute a local model and then use some aggregation algorithm to aggregate the parameters from the local models and obtain a global model that depends on the input of all participants. So there is a work from Google from 2017 that implemented such an algorithm, and it showed how its efficiency scales with the number of small devices that are participating and with the length of the vectors that model the parameters. So you can see that even if you have 500 clients and the length of the vectors is 500,000, the protocol still runs in a few seconds and seamlessly handles dropout of the parties in the protocol. You could also consider the same question, but with a little bit different architecture, where instead of one party, you have multiple servers that help you do this processing, and also add the addition that each party, apart from each small device, apart from contributing its input, also gives a proof of its validity. For example, proving that it's within a range. So there is a very nice work from Stanford from this year that implemented such a protocol, and this protocol is actually being deployed in Firefox. And here is an example for the overhead that this solution brings in terms of the slowdown of the throughput that can be handled by the servers. And you can see that this is the case of training a d-dimensional least square regression. So depending on the dimension, the slowdown goes from 5.6 times to 11.6 times, but you're still able to handle between 1,000 and 2,000 requests per second. So now that we have looked at these settings of computing aggregated functionalities, we can also ask a different question. Now that we have the output of this aggregated functionality, does this output reveal anything about individuals who are contributing data? And here we meet the notion of differential privacy, which exactly tries to construct algorithms that give us such type of guarantees. And there are 2 main scenarios for which differential privacy can be defined. One of them is called the central model, which assumes that we have a trusted aggregator that has access to all the private inputs coming from the individual contributors. And this trusted aggregator computes aggregated functions and releases them. And the goal is to argue that this output of the aggregated functions do not reveal individual data. And differential privacy develops these mechanisms that capture this intuitive notion by saying that the output of this aggregator function on neighboring databases that differ only on a single record will be close. And this closeness is parameterized by a parameter epsilon that will be used to trade off between privacy and utility in these mechanisms. The other model for differential privacy, which is called the local model, no longer assumes this trusted aggregator. In this setting, each party has to locally randomize its input before sending it to the untrusted aggregator, and we want to maintain the same type of privacy guarantees with respect to the individual contributors. And as you can see, this setting of the local model matches much better the setting of federated learning, where our central server is also our adversary from which we want to hide the privacy of the individuals contributing their inputs. So there has been a lot of work developing general differential privacy mechanisms in the central model, as well as specialized methods for particular functionalities of interest. But since the local model has been more relevant in this setting of federated learning, this has been where some of the companies have been looking at, and Google and Apple have been leveraging some local differential privacy techniques in order to aggregate, to collect aggregate statistics. And the challenge really here is to achieve good trade-off between utility and privacy, because in general in local differential privacy we need to have more noise to protect privacy compared to the central model. And this framework that came from Google, which is called Rapport, has turned to be the main example to compare against when you are developing new local differential privacy techniques. And in the next two examples that I will show you, we have seen some work that improves on what has been achieved by Rapport. So this first example comes from NeurIPS in 2017 and has developed an algorithm that detects heavy hitters using local differential privacy. And the result in this work improved the total work that needs to be done by the server while meeting the worst case error that has been proven in these models. And as you can see from this result, you can see comparisons between the estimated frequencies using this algorithm compared to the exact frequencies in a data set of 10 million samples with about 26,000 unique words. And you can see that smaller values for epsilon mean more privacy, and we expect that this is where we'll have more error in terms of the utilities. And you can see that this algorithm performs quite well for counting the heavy hitters for different, going from the most frequent items, even also in the setting of the less frequent items. And the main comparison against Rapport really comes when you're looking at the less frequent items, where this new algorithm comes much closer to the exact values compared to the Rapport estimates. Another work from Usenix 2017 also develops a general framework for local differential privacy that improves the choice of parameters, and as a result of this achieves better trade-offs between the privacy and the utility. And what you can see from these graphs is that as you increase the epsilon value, which means that we reduce the privacy guarantee, it achieves smaller errors and at the same time achieves higher true positives. And when we are talking about this comparison between the central and the local models for differential privacy, a natural question is to ask whether we can use secure computation techniques to get the best of both worlds. And what I mean here is to get the utility from the central model while providing the privacy guarantees from the local model. And there are generic constructions that compose the two, but oftentimes these are not the most efficient. And some new model that has been introduced this year, which is called the shuffle model, has an interesting observation that if you take the inputs that are coming from the local model, or the ones that have been locally randomized by each of the parties, and you shuffle them randomly before sending them to this untrusted aggregator, you actually need to add much less noise in order to achieve the same level of privacy. In particular, you need to add only logarithmic noise in this shuffle model compared with the local model where you need square root noise. And this new shuffle model has been used also in a new work coming from Google, which is called Proclo. And there, the shuffle algorithm has been implementing using SGX, and they have demonstrated that this performs much better than rapport in terms of detecting how many unique words, for example, are coming from the inputs of these small devices. And also, when we're talking about this amplification from GP and MPC, I also wanted to point out a new interesting work that came from BU this year, which also has a very interesting title, Turning Hate into Love, where love stands for large-scale one-server vanishing participants efficient MPC, or more or less the federated learning model that I described. And hate is a new primitive homomorphic ad hoc threshold encryption. And then they demonstrated how you can construct these federated learning protocols from this new primitive and give you different instantiations of this primitive. And also their protocols meet the lower bound that they can prove for this model in terms of how many messages you need to exchange. Okay, so this also brings us to the last primitive that I want to tell you about in this talk, which is zero-knowledge proofs. And zero-knowledge proofs help us prove that we know some secret without revealing it. And for example, if we have this small device and it wants to send an encryption of some input, but at the same time we want this device to be able to prove that this input is within a specified range. So why do we want to use zero-knowledge proofs? I assume all of you know their application in the context of blockchain, of proving properties about encrypted data, but this is by far not the only interesting application of zero knowledge. As we saw in the context of machine learning, you can prove properties about your inputs. You can also generate proofs that you have correctly run the training algorithm for a machine learning algorithm or the evaluation with respect to a commitment of on certain data. And when we talk about zero-knowledge protocols, there are several efficiency properties that we should be thinking about. This include the prover's efficiency, the verifier's efficiency, the succinctness, which means how long are the proofs, whether our protocols need interaction between the prover and the verifier, and finally, whether we need trusted setup. And what does trusted setup mean is that we have some phase in which we need to embed some secret in what we call common reference string. And it is very important that this secret remains hidden from anybody who will be generating proofs because the soundness of our proofs will depend on this secret not being leaked. So in this, with respect to this trusted setup, I would like to distinguish SNARKs, which means succinct non-interactive arguments of knowledge, versus other techniques for zero knowledge. Because as far as we are concerned with existing constructions, all SNARK constructions require trusted setup. And we have some new work on hybrid constructions that offer you dual mode of execution, that it could behave either as a SNARK or as a non-trusted setup system. But let's look at these two major types of zero knowledge. So if we want to talk about zero knowledge SNARKs, then most of the existing constructions leverage technique which is called quadratic arithmetic programs, which we introduced a few years ago. So there are several systems that implement this main technique in various different flavors, starting from our work Pinocchio, and maybe the most widely used one nowadays, which is LibSNARK. And in terms of what is their efficiency, I will give you an example from a paper from Usenix this year that introduced ways to parallelize the computation on the prover. Note that in the case of SNARKs, since the proof is so short, usually the verification time is very efficient, and the optimization goals are on improving the runtime of the prover. So this paper achieves prover time that takes 10 microseconds per gate, and the verifier time is also very fast. So if you want to look at specific applications, if you want to generate a proof for the correct training of linear regression on 20,000 points in dimension 500, this takes about 95 seconds. If we want to look at zero knowledge without trusted setup, then we have a lot of trade-offs between the proof size and the verifier's work that are between logarithmic and linear. There have been many approaches to construct such protocols. Some of them are based on discrete logs, which include bullet proofs, which has been a paper with lots of applications recently. There are MPC-based approaches, such as ZK-BOO and Ligero. Then there are some other techniques that I put in the category IOP-based techniques, such as Hyrax, ZK-Starks, Aurora. So here I have some graphs from the Hyrax paper that really show that there are many different trade-offs when you look at these systems in terms of proof size and verification and prover efficiency. So you have to be very careful with respect to your specific application, what you choose. These numbers are for proving knowledge of assignment corresponding to the root of a Merkle tree. So you can see what's happening here. And since I'm running out of time, let me try to conclude. I tried to give you a few examples from techniques from advanced cryptography, which all of them are accompanied by implemented systems. So how can we use this advanced crypto? So a word of warning is that none of this system is really out-of-the-box use system. And there are good reasons for that, because sometimes hiding complexity in order to facilitate usability also sacrifices efficiency. And in many of these scenarios, we cannot afford to do this. We really need to squeeze every last bit of efficiency. So if you want to use these systems, you really need experts, even for choosing your parameters or for doing comparison across different frameworks. The implementation code is research level code, so it's definitely not production level code. If you're interested to learn more about these techniques, there are ongoing standardization efforts in the area of zero knowledge and fully homomorphic encryption. And also there are some links that give you a starting point to learn what's available out there for MPC, DP, and zero knowledge. And since I started by saying that the inspiration for my talk was Shai Halevi's talk, let me finish also with something from his talk, which said that it's really time to put to use these techniques in practice. So I would like to thank you and take any questions.
Thank you. We have time for 1.5 questions. Okay. I'll ask questions. What's your favorite open questions?
What's my favorite open question?
What would you like to solve in the next 3 years? 5?
I mean, it's interesting to put together a lot of these techniques. So if you're thinking about the question of federated machine learning, right, we are still kind of struggling to compose in a very good way differential privacy and MPC. And also there's the space of bringing zero knowledge in terms of guaranteeing correctness for the inputs. So I think combining and developing these systems that will have very, I think, huge impact in practice is something that's still an open question for me. We have some promising starting points, but there's lots of work to do in that.
Okay, thank you. Thank you. I'll give you 5 minutes for your 32 minutes. So I will leave 3 minutes for questions. She took it. She stole it.
And which one is
For the north. Okay, so the next talk will be deploying MPC for social good, and the speaker is Lucy Chen.
Hello? Okay. Hi, I'm a research software engineer at Boston University, and I'm going to focus on one of the techniques that Mariana just spoke to and mention how we've used it in practice. So I'm speaking today on deploying MPC for social good. So I want to begin by highlighting a variety of different applications that we at Boston University are collaborating on in the space, specifically of MPC for social good. So from enabling joint medical studies to allowing social scientists to share research data, to protecting data of those recovering from opioid addiction, there is a wide array of societal problems that can significantly benefit from the use of MPC. However, the work needed to actually go from taking an idea to deployment involves a lot of important work that happens outside the scope of the cryptography itself, which will be the focus of my talk. So today I'm going to focus specifically on 3 use cases and deployments, and begin with a study on pay equity. And to make sure we're on the same page, secure multi-party computation, or MPC, is a cryptographic technique for computing some function f over private inputs while yielding a public output. So our work in MPC began with this story here. In 2013, the mayor of Boston at the time, Mayor Menino, set out to make Greater Boston the premier place for working women in America. And he wanted to do this by removing the visible and invisible barriers to female advancement. So this later led to the creation of something called the Boston Women's Workforce Council. And this council seeks to, 1, understand the root causes of the wage gap, 2, work towards closing that gap, and 3, evaluate the success in doing so. So currently there are over 200 businesses in the Boston area that have signed on to a compact with the Boston Women's Workforce Council. And in this compact, they agree to contribute their salary data and also to a number of other initiatives honing in on best practices toward actually addressing the societal issue. So we at Boston University have been working towards enabling this data contribution process by using MPC to protect company-level data while still allowing aggregate data to be brought forth to the public for analysis and for us to really understand the wage gap itself. So in the originally proposed workflow of how Boston wanted to conduct a study of this level, they wanted each business to submit their data in the form of spreadsheets in its raw form to a trusted third party. And that trusted third party would take all of that data, do the proper analysis on it, and generate the results. However, the lawyers at these companies were weary of any entity receiving that raw salary data, no matter how trusted they actually were. And also, the trusted third party later backed out for similar reasons. They were also afraid of a data breach, and they didn't want to be sued potentially by hundreds of different companies. So this is where we got to MPC. So our team proposed an MPC-based solution, and as shown by the challenges in the originally proposed workflow, there are a variety of different concerns coming from the perspective of different roles involved in this type of study. So our MPC-based solution has taken into consideration all of these concerns in order for successful deployments to actually happen. So first I'm going to talk about the lawyers' concerns. As I mentioned, they are very concerned about liability. And the protocol itself thus federates trust between Boston University and the Boston Women's Workforce Council. So individual level data can only be revealed if the two of us decide to collude. And I argue that neither of us are incentivized to do so for the good of both of our reputations and for the cause of the actual problem. So the Boston Women's Workforce Council itself is concerned with participation. They want as many companies in the Boston area to sign on and actively contribute their data towards this initiative. So therefore, the solution has to be easily accessible by a wide range of different companies. So here we have hospitals, law firms, financial firms, all contributing, and they have different types of corporate environments. So therefore, we can't do things like set up servers on specific ports or run virtual machines or have to manipulate different things involving their firewalls. So we chose to use a browser-based solution since hopefully everyone has a browser. And all of the code here runs in the web client. So the HR and diversity personnel at these individual companies is the person who's actually contributing this data and using the platform and going through this process. And they want to make sure that the process is as easy for them to navigate and that they can correctly contribute their data. So we have thus focused very heavily on the usability, and we start out by first using a standardized template that is familiar to them. And they already use versions of this for regulatory purposes. And we're also continually working on a number of different things to improve the usability of the platform, which I will speak to later. So lastly, we have the IT personnel at the companies who is interested in verifying the code itself and making sure that it provides the security guarantees that we claim that it does. So therefore, our code is open source and available on GitHub for anyone to audit. And we have purposely written it so that it is as clear and concise as possible so that it is easy to verify. And in managing all of these concerns of the roles, there is another element of simplicity that I want to emphasize. So we use an additive secret sharing scheme under a semi-honest threat model. The protocol here itself has existed for some time now, and there is nothing really new in it itself. And there are definitely more technically sophisticated platforms out there that deal with these complex issues of scalability and performance that come along with MPC. But as I mentioned, the simplicity here is really intentional. We need to be able to explain the solution to CEOs, lawyers, to all the different roles that I just mentioned. And they have to be successfully convinced enough to want to give over their data to us and believe that it really will be protected. And as you see here, we add a random mask to the data, which is passed along to Boston University, while the masks themselves are given to the Boston Women's Workforce Council, therefore segmenting trust. And the image here is the actual explanation that we use to the various different types of people that we need buy-in from. And we have been successfully able to do this to actually get them to agree to this contribution process. And we also hold training sessions where HR and diversity personnel can attend, ask questions, and be walked through the submission process itself. And here is a stripped-down version of what the platform actually looks like. You can see the full thing at 100talent.org. So each user is given a session key and participation code. As I mentioned before, there is a standardized template that they receive in Excel form, and they can pre-fill it and then drag and drop it here, and it'll autofill all of the fields necessary. Or they can go through and fill out each cell in the spreadsheet manually on the platform itself. So this screenshot only depicts total annual compensation, but we have also gathered aggregate data on performance pay, which measures bonuses, and also the length of service to get a more granular look at this problem itself. And we also gather data based on race and job category, so we can look across the different levels from executive down to more entry-level positions. So an interesting lesson we've learned here is that we've had to be very specific about the language we're using when we actually explain what's going on the platform. So words like upload or submit have a general connotation of giving over data in its plain text form. But here that doesn't happen. It never leaves the actual browser in that form. So we do not use the word upload in the drag and drop box here. We also had to very explicitly state what submit means in this specific context. So since recovering mistakes under MPC can be expensive, we have added error checks to help make sure the process is as error-prone as possible. We have information about what the upper bound on certain metrics might be given the cohort of different companies that do participate in the study. So therefore, we can provide warnings when numbers exceed that upper bound, and we also provide checks to make sure that the format itself is correct before we allow users to submit. So as you can see here, there are a number of errors that can be triggered, and they all have to be cleared before the user can actually submit their data. And we also provide something we call a totals check. Throughout the process, we just count up all the different personnel that were included in the data, and therefore employees can look at that and have a sanity check of whether the total actually matches up with their organization. So we do also allow users to resubmit their data and overwrite whatever has been previously submitted in case there is an error. And we conduct this MPC submission process over a period of a week, so if they discover something on day 2, they can still go fix those problems and then submit later on. So as I mentioned, we want to emphasize usability for the employees actually submitting the data. As part of this process, we ask a number of high-level questions, such as the relative ease of preparing the data for submission and the type of training that they've had in doing so. And the answers to the survey responses here are also seeker-shared. We have also been interested in getting more granular level data on the user experience itself, but we can't use a third-party web analytics engine like Google Analytics without potentially revealing data. So therefore, we've added some basic web analytics, such as errors users encounter, the average time spent, and mouse movement into the MPC protocol. This data is secret shared along with the actual data about the salaries and the survey questions that I just mentioned. And this is only seen in aggregate form. So the picture on the right here shows the mouse movements from a mechanical Turk study we conducted using this method. Moving forward, we want to A/B test our platform to have a better understanding quantitatively of the user experience. So because of the security guarantees that MPC provides, the work done in addressing the wide spectrum of concerns from different roles involved in the study, we have been able to successfully deploy this twice now. First in 2016 and again in 2017. And in 2017, 114 employers participated in this, and that accounted for 16% of the workforce in the greater Boston area. And we are once again deploying this in fall of 2019. So the results here are unsurprising, and if you're interested in learning more about what the wage gap problem looks like in the Boston area, you can feel free to read the reports that the Boston Women's Workforce Council puts out based on the results of this data itself. So, and although studies have been done in the past on wage equity, we are able to gather data longitudinally with more participants added each year. As our mayor, Marty Walsh, notes, in 2014, there were only 38 companies committed to this study, and now there are over 250. And since the study occurs periodically, we are hoping to gather data on specific cohorts over time to be able to assess if the wage gap is widening or closing as different practices are implemented. This also helps us actually drive accountability towards addressing the problem, since we're seeing the different effects over time. And the data itself, because of its granular nature, can help drive a more nuanced discussion of the wage gap in Boston. We are able to see where the gap is wider and how that varies by job and race. And in the next deployment, we're also working towards industry-specific breakdowns as well, so we can compare different industries and how they match up with the average. And the granularity of the data also allows us to get more specific about the solutions and allows us to address the places of the grossest inequalities. And of course, although the MPC is an important piece in gathering this data, it is only part of the broader solution towards this societal issue. The Boston Women's Workforce Council is involved in making connections with all of these companies, hosting workshops, and hearing from the businesses themselves on the roadblocks that contribute to pay equity. They also talk about best practices toward advancing women in the workforce as a whole. So this data can help drive the conversation, but that conversation still needs to happen between actual people coming together to discuss the changes that need to happen in the workplace. And with that, I want to discuss another use case of MPC in the city of Boston that we have been involved in. So we're working with the Greater Boston Chamber of Commerce on an initiative to promote economic inclusion. Companies are expected to increase their supplier diversity here by supporting local women and minority-owned businesses. And we collect metrics similar to the other study in aggregate form on spending toward these types of businesses versus total spending by these companies as a whole. And right now, there are currently there are more than 10 companies participating in these deployments, so it's happening at a much smaller scale than the pay equity study, but we've been able to repurpose the same platform for that study here with a simple configuration file. And we've also applied the same lessons we've learned in usability and accessibility and auditability and in how we've been communicating MPC to allow for successful deployment to happen. And this was first deployed last spring, and we're looking at an upcoming deployment in March. And so now I'm going to switch gears and talk briefly about a different use case in detecting serial perpetrators of sexual misconduct. So Callisto is a nonprofit that creates technology to combat sexual misconduct, and they first created a sexual assault reporting tool on college campuses. So with that platform, they were able to see some really great impact, where students were 6 times more likely to report through Callisto, and they were 3 times more likely to seek out medical and emotional support. And they also found that 15% of the survivors using the tool were actually able to be matched with another survivor that named the same perpetrator. Going off of the Me Too movement last year, Callisto wanted to expand this work and detect serial perpetrators in industry settings in a way that was empowering for survivors. So they were interested in a cryptographic approach that could stop the spread of sexual violence while protecting the privacy and civil liberties of both the survivor and the accused. So this is where myself and some others come in on the crypto side of things. So we worked together with Callisto on a design and implementation that guarantees that identifying information about a survivor and accused can only be decrypted by a lawyer when at least 2 users name the same perpetrator. So I'm going to describe a very watered down version of the design, omitting a lot of the details here in order to just highlight a few key takeaways. But for more information, you can refer to the white paper shown here. So let's say Alice and Bob name the same perpetrator. The same key is then deterministically generated. This key is then used to help encrypt any identifying information about either of them and Mallory. So let's say we have another user here, Carlos, who names a different perpetrator, Eve. An entirely different key is then generated. And through the use of an oblivious pseudo-random function with 2 different servers involved, the slope and intercept values here for Shamir secret sharing are generated based on the perpetrator identity. So as I mentioned, this uses Shamir secret sharing with a threshold of 2, and the secret of the perpetrator identity is embedded in the slope and the key, which serves as the y-intercept. So Alice and Bob then have the exact same slope and key values, but differing hashed user IDs, which ultimately generate different y values. And these x and y values then represent Alice and Bob as shares that can be used to reconstruct that original key. This then reveals that key, which we can use to decrypt information about the users and the perpetrator. And as you see here, Carlos, who named a different perpetrator, Eve, cannot be used to construct the key in the same manner. Oh, and I wanted to point out there are other techniques involved that I have not mentioned, so once again, refer to the white paper. So I wanted to bring up this example specifically because it is another deployment where the crypto has been successful in tandem with advocacy. And that advocacy work is rooted deeply in understanding the population that the technology itself serves. There is important work happening from Callisto on trauma-informed design and making sure that the process itself does not re-traumatize the user who's using it. And they've also put out a survivor guide that enumerates different resources outside of the technology that users can benefit from. And there's also real empathy because of the work Callisto has already done on college campuses. They're building off of information and lessons learned from that process, so there is a credibility and human sense of trust. So the crypto code here is also open source and auditable by anyone who would like to view it. And of course, the crypto on its own would fail to take on a life without all of this work that has come before it and also along with it. And this touches back on the same critical pieces of work that needs to be done on the usability and accessibility side and in making sure you are fully communicating the guarantees to your users. So hopefully I have demonstrated that MPC has broad appeal and applicability to a variety of causes and fields. The techniques I've mentioned, like additive secret sharing or Shamir secret sharing, have existed for decades and are not necessarily novel, but they do show how even very simple protocols can have a huge impact when joined together with strong partnerships and vital work in addressing all of this stuff outside of crypto, such as the usability, accessibility, and auditability. So I'm really excited about the place that MPC can be applied to help tackle different social problems, and I hope you are as well. So, thank you.
Thank you. Questions?
Hi. First, I just wanted to say thank you. This sounds like fantastic work, and I'm really glad that people are working on it across both the advocacy and the technical side. And that's part of my question is, in the first case study where you talked about with the sharing of the salary data, you can very easily imagine that the lawyers get together and just say, no, this isn't going to happen. We're not going to give it to any third party. And obviously, you need some trusted third party in order to do this, so the whole project is shut down. How did that gap from that business side of it to, like, how did anybody think, like, maybe somebody at Boston University knows a way that we can do this without sharing the data? Like, how did that happen?
Yeah, so I think it took a lot of work on our team to, like I said, to make sure we're communicating those guarantees very properly. So I think we've done a lot of iterations of how we explain MPC and additive secret sharing itself. So we've tried out different graphics, different visuals, and throughout time have refined those more and more. But yeah, it's just a lot of making sure that you're testing out different ideas and seeing how they click with the exact users or I guess in this case, the lawyers that you're speaking to, and really honing in on what their concerns are.
I have really cool work on the Callisto system. I had a question. Who enters information into the system, and what prevents like a party just like trying to probe and exfiltrate information out of that? Is it access controlled in that you have to be a lawyer to enter information into it, or?
No. So the individual users are the ones entering their own information, but the lawyers are the only ones who can actually decrypt that information. And they each have their own private keys that are necessary before they can even access the platform itself.
Okay, thanks.
So multi-party computation requires a bit more math than a typical stakeholder would be familiar with. Did you have any difficulty explaining to them what you were doing and getting them to trust you?
Yeah. So that's where we really have to go back and focus on these types of visuals. So we've used things in the past like perhaps like cakes, so demonstrating it in something that's less focused on math and more something that's a bit more tangible. We've also used different levels of bar graphs and showing how if you take one bar graph and then you subtract out some other bars from it and something of that sort, showing the end results. We also have some paper demos that we run through with people where we have them write down their own secret number, have them pass that sheet of paper along to someone else, have them add a mask, and repeat this process and allow people to ask open-ended questions about it.
And to follow up on that, did you have very many people you met with, very many decision makers who just never came around, who remained resistant to?
So there are some people who, on the opposite side of things, have agreed to participate in the process, but then done things like give us an NDA for the data when we've gone back and said, hey, we don't have the data that is actually the core guarantee here that we're making. So we've definitely seen stuff like that.
Thank you.
Any other questions? Oh, actually, this one.
So I was wondering. Is it better? Okay. Yeah, thank you for the talk. It's very interesting. So I was wondering, is there a chance that an employee or the HR personnel could submit the salary information, which is not exactly the information that goes to the pay slips of the employees? Like, can they submit wrong information just to show that they are like providing equality in terms of wages? Like,
sorry, I couldn't hear the entire question. Would you mind repeating it slightly louder?
Oh yeah, sure. So is there a chance that an HR personnel submits salary information, which is not the actual information that goes into the pay slips that are in the pay slips, just to show that they are providing equal wages, but they're not actually? So is there a need for verifying the salary information?
Yeah, I think that is something that would be ideal. So actually, because of the way that the Boston Women's Workforce Council communicates with these companies, that's not something we're able to provide. So the companies can choose to contribute their data or not. As you saw, there were over 250 companies actually in the compact, but around half of them actually contribute data. So some of these companies want an element of being able to say like, hey, we care about this issue, so we're going to be in this compact, but we're not part of this data that was actually in there because we're doing well. So they want that ability to have an out in that manner. So therefore, we can't actually verify who is in the data set and who has contributed data. And because of that, we also can't verify any notion of correctness. So for things to move forward in that fashion, there would have to be some changes in the communication with these companies and changes fundamentally in how the compact is structured.
Thank you.
Thank you, Lisa. And the next talk. So the next talk is towards transparent zero-knowledge computation, and Kurt Nielsen will give the talk.
Yes, 2 seconds.
You know, 5 minutes.
Yes, okay. Yeah. How much time do I have?
Leave 3 minutes for the talk, so we have 32 minutes.
32 minutes, perfect. There you go. Okay, thank you. I will continue the talk about how to convince people about using this fantastic technology, zero knowledge computation or multi-party computation. So I'm not a disclaimer, I'm not a computer scientist, I'm an economist, but I heard about this technology 15 years ago. I was convinced about this, and as a researcher, we raised money, and 5 years after, we created the first use of this technology, which was commercial use. And the company that used this wanted to buy the solution afterwards, so we did a university spin-out, which is Patricia. And what I will be talking about is what we have been doing and trying to convince people about buying into this technology and use that for a number of applications. Yeah, that's basically the talk, and it has been used commercially for 10 years by now. So it's not new yeah, it has been used basically. So let me just talk to some of the challenges that we have been facing. So clearly, doing computation in a black box like MPC requires to convince people about what we're actually doing. So transparency and the platform that we're using is super important. So the first case that we had was very tangible in terms of running a multi-party computation. It was an industry setup. Some contracts needed to be exchanged among buyers and sellers, and each of the parties, you can see the pictures there, they came with their own laptop and a USB stick with the cryptographic materials. So it was very tangible that they were connected, these three computers, and we computed the clearing price. So this application is actually a distributed exchange. It was a standard exchange mechanism that was implemented using this technology. So that was the starting point. Sorry. That was pretty slow, but running an auction like this was not really an issue because there was plenty of time to wait for the result, even though I think it took 15 minutes or so with everything. Since then, the protocols has improved tremendously by the contribution from a lot of you. And that sort of leads into or makes it possible to apply the technology to other applications. And that's what we have been trying to do. So definitely doing more auctions in the beginning, moving into key management, doing more statistics, and so on. So that's one side of it. The other side is to move into platforms that are more scalable, but maybe also a little less transparent, using cloud computing. But you could run it on separate cloud service providers, at least to signal that it's truly distributed. Or what we are doing recently is to use blockchain technology to have maybe create some more transparency. That's at least what we will claim. And done right, I guess we can also get this to scale. I'll be talking more about this. But basically, one of the challenges is that we are selling trust, so we have to convince people that it's more trustworthy to distribute a system instead of just pointing or basically counter-bribe a consultancy to do a trust to solve the job as a trustee, and that is a challenge. It clearly is, and when you convince them about that, then the next question is who should actually run the nodes. So the initial case where we had some natural groups of persons, buyers and sellers, you could basically hand a node to each of these groups. In other cases, you might not know a priori who would be the opposing interest in this setting. So you need some nodes. And that's just continues to be a challenge, but that's also some of the things that we are struggling in solving. So let me introduce, so what we have been doing is that we started Patricia 10 years ago, and then we tried to sort of sell the big vision, and which was difficult at that time. But that was people who saw the use of having a distributed auction, and we found the first industrial investors, did a cloud solution on auction systems, and then we moved into key management, got the first institutional investors, and along the way we have been looking a lot at statistical solutions, and that has been that's something that we have spun out in a separate country, a separate company recently, and what we are doing now is actually to combine some of these resources that we have been working on into something they called privacy blockchain, and I will talk a little more about that in a minute. So basically, I want to sort of walk through some of the applications that we have been doing and then go back to this idea of privacy blockchain and maybe try to convince you why we need an infrastructure like this. So the beginning was auctions. So you basically remove that weak third-party institution, distribute the auctioneers, to make the institution more trustworthy and maybe also more cost efficient. And that's what we have been doing, selling various commodities like spectrum rights used for telecommunication, rough diamonds, working on a high-stake auction for rough diamonds, working on electricity auctions. So it solved a problem in that space. A similar type of mechanism is matching, and a case that we are building as we speak is off-exchange matching, or basically what is known as a dark pool. So we take the dark pool operator and distribute that. One of the challenges with these dark pools is that if they get hacked, you get a lot of valuable information, and so they are an example of a vulnerable third party in the financial system that could be improved by a distributed setup. That's also gave us a lot of challenges. So the requirement was high. This should be run really fast. This should be fault tolerance. They wanted as many nodes as they could get. So I think we ended up passing the requirements with 7 nodes. And this technology is now been moved into blockchain. So this is also becoming a blockchain application, because the design is really, this institution has been designed to help institutional investors trade on financial markets, but smaller buyers and sellers are meeting the same challenges in selling crypto assets in the blockchain space. So that's what we are trying to solve with this solution. That will be a separate entity. Well, that will be announced relatively soon. So that's the market design solutions. in terms of statistics, we've been focusing on privacy-preserving statistic in different settings. The first one, the one to the left, is a very I think interesting case. So this is about the Danish statistics, and it's about the Danish healthcare data. That is two public registers that has never been combined. They're not allowed to combine these, but now they see the opportunity to use a two-party system. So they can claim, okay, they don't really combine the data, but it's still making them available to run analysis on these combined data, healthcare, socioeconomic data, which is clearly highly valuable, especially because in Denmark, where this is happening, they have registered all citizens from their birth for the past 50 years. So there's a really long track record on an unbiased sample of the population. So you can imagine a number of scenarios in pharmaceutical companies coming in and simulating a phase 2 trial, which is super valuable if you can detect some challenges with a new drug at an early stage and things like that. So, but this will be some very controlled type of computations where these two public registers, they will look at the computation that you would like to run, and they will say go and no go, and then you can run the computation and get your aggregated statistics at the end. So that's one case. The other case is another blockchain application, which is basically disrupting the data broker. So it's a decentralized system that give control to the data subjects. So you as a data subject, you can sell your data to a data requester. So the use of MPC in this is that that's running a number of two-party matching of the requester's needs and your personal data. And if you match the criteria, then you get to trade your data in a token economy. So that's basically what it does. Distributed system that removes the middleman as a data broker and distribute it to the individual data subjects. And that's the thing that this technology can do. So the last, this one is basically threshold cryptography. It's solving things like more secure solution for crypto wallets, more cloud-based key management systems, and we actually have the full a number of people from CPO here today. So just let me know if you want an introduction. So that's sort of some of the basic things that we've been working on, and as I mentioned, there's actually crypto blockchain application in each of these fields: market design, statistics, key management, and what we have been working on for the past year or two, and that we want to combine, and the insight that we have achieved by this work, we combine that into this new project. So we have that the key management is actually a component in these solutions, and the first two applications, which is the matching and the data broker, the distributed data broker, is two nice examples of what you could do with an application, with an infrastructure like the one we want to construct, or is basically constructing as we speak. We just want to make it easier for people to create applications like this in the future. Yes. So blockchain and privacy might be sort of an evolution, and what we're focusing on is basically step 3, so where you have a lot of information involved from many users. So using zero knowledge proof is not feasible. You need something that are more flexible, that can do generic computations. And that's basically what this project is focusing on. Whether you believe in this vision or not, it's at least something that is being articulated. The Web 3.0, where you get some sort of a blockchain computer, and to have this to solve real problem, you definitely need serious privacy measures, and that's what we are trying to add in a distributed fashion. So going back to that infrastructure, from our perspective, it's basically three things. So you have the ledger, you have the smart contracts, you have the privacy measures, which is basically what you would need to solve a number of problems. And I will come back to that, try to argue what is the class of problems that we are focusing on. So just two more words about this infrastructure. So one thing is the nodes. So you have the blockchain, which we're just not really changing anything, just taking the best practice blockchain. But that's sort of a separate job to solve as a node. Then you have this what we call CK computation, which is MPC, which is it's a separate task for these nodes. And typically you have large networks for the blockchain infrastructure. For the MPC, you will have smaller ad hoc networks. So you need and you need to separate these two, and they need to collaborate to get the synergies out of these two different networks, and that's what we are struggling with. Getting that in place, it's really all about orchestration. Make it simple to come with your problem, get a provable secure protocol. Delegate trust in the system, and then get a efficient, simple, and robust execution, which is what we have been working on for these past 10 years, and also met other requirements than just getting it to run fast, like robustness, what happens if the node is not available, and so on. So that's the infrastructure that we are working on, and the next slides is actually some sort of an attempt to come with a class of use cases that needs what we would call privacy blockchain. So as an economist, it's really all about taking decisions. So you have two components. You have alternatives, and then you have some preferences on these alternatives. So getting this big data or getting more data about the alternatives as well as the preferences, of course, makes it possible to make better decisions. If you take into account the complexity of these decisions, so you have the overall strategic decision, you have the other end, you have automated operational decisions that hopefully move you in the direction of your strategy. So that's one problem to solve. And then everyone is part of some strategic interaction with a number of other partners. You have privacy concerns. There are regulatory concerns. There's a number of concerns about these data that realize these better decisions. So somehow we need to mitigate between keeping these data private and to use the data to make better decisions. So that is, of course, some core stuff for economists, and this resource is actually one of the starting point for Patricia, and it's resource from 1979, so it's nothing new. It's a revelation principle, and it's kind of a nice small resource that says, okay, you can have any mechanism. If you could instead of you being the strategic player, you basically just tell the truth to a impartial, trusted third party that behaves in your interest, and it's relatively easy to see that can always be better than any mechanism. So that's what economists have used as a sort of theoretical basis for creating mechanisms. So this is a sort of the starting point, and then you try to create your mechanisms that solve the real world problem. but that's your benchmark, and it's been more like a construct. So personally, when I heard about this technology for the first time, it didn't take me many seconds to realize that this would be a fantastic technology, which if you actually have what is called the social planner, the impartial, trusted third party, then you could basically allocate the resources in a more efficient way in general. So I personally think this is a very strong argument for using for MPC. So, and that's mechanisms, and mechanism is actually a way to sort of navigate between ways we use to organize the economy. Could be a contractual relationship, could be the society as such, whether it's a decentralized or centralized system. If you have an auction, you actually set up the rules for how to do how to facilitate competition. That solves some of the basic problems that you have in the economy, whether you are in a decentralized or a centralized world. So there's a lot of there's consensus about these problems. Whether you have the decentralized, you will have the market failures. In the central world, you will have the governmental failures. And in both of these, well, you have lack of information, which is creating a lot of these problems. So that we are solving with the big data. We get the artificial intelligence, so we can map these preferences, map the alternatives, and just put them together, and here we go, and we all have better decisions. Except that there is some concerns. So the first one to the left is Google Trend. It's artificial intelligence competing with privacy, who's interested in most. And on the other side, it's just one of these many studies on trust in general, trying to ask people about their trust in institutions, in academias, in researchers, in global companies, in governments. One of the challenges here is that the global companies and the governments, which are usually those that would set up a system like this, is not the most trusted institutions. So you might actually need to maybe rebuild or build trust, and that the argument would be that that really requires some strong commitments. And that's where cryptography comes in. If you commit to a cryptographic protocol, let's say we're arguing for the no single point of trust, that's really a strong commitment. And use that to rebuild trust. So I think is where cryptography has a super important role in fixing maybe some of the most basic problems in most societies, maybe at the moment, at least an increasing problem. So back to the infrastructure with the three components, the information that is publicly available, the smart contracts run computation on these information, and the privacy measures. You can actually implement these mechanisms that that provide incentives for people to make better decisions. You can combine this with when you have all of this and data and analytics and these mechanisms, then you can make these better decisions in a combination of these two technologies, blockchain and CK computation. So maybe 2 words about the type of market mechanisms or solution that you would typically look at. So you would either consider some non-cooperative solution, where you're competing about winning an auction, competing in a negotiation. There's a number of different non-cooperative games. But there's also a huge class of cooperative games, which is maybe the class that could gain the most from an infrastructure like this. And it's actually also, in most cases, where you can get the most values out of a collaboration by finding the coalition, finding the right person, and make them collaborate. There's a number of examples of this. Farmers have done this for many years. I think I come from a country where this was like 150 years ago. This is probably the basic of the wealth generation, that some small poor farmers went together and bought the equipment to process the milk and the meat, and then they actually managed to create a lot of wealth this way. That could have gone wrong in many different ways. So you needed to concentrate all the wealth, and if they have had corrupt managers that was just running away with the money, then that would not have happened. So that you could do with an infrastructure like this. You could make sure that you find the coalition in a privacy-preserving way, and then implement the cost-sharing scheme or the revenue-sharing schemes. That one example. So it doesn't have to be small players. This is another example of the largest shipping companies that are too small for certain jobs. So they do what is called tanker pools. They pool the different ships that they have for certain jobs and run a cooperative, basically, a cost sharing and revenue sharing scheme. Taxi drivers, another example. And then you're moving towards the non-cooperative solutions. Energy system, you need to make more room for renewable energy. You need to combine a lot of resources. That also requires a lot of information and a lot of price setting. Supply chain, clearly. Bidding, auction is some of the two. Negotiations, mergers and acquisitions. So this is some of the example of classes of problems that could be solved by an infrastructure like this. So but we are still back with some of the basic challenges that we and those of you who have been trying to solve this, most likely, I would imagine, has faced. That you need to find those that is running these nodes. And if you have a situation like the one with the data broker, you might have some natural opponents like the data requester, the data providers. You can run, you can set up the system to run a number of two-party problems. You might have other situations where that is not possible. So for the most of these cases, you will have a generic use case where you will have a lot of players in the beginning, a lot of information, then you'll find some matches, and then you should execute the decisions. So in the first step, you might need to delegate the trust to some more generic type of nodes that could be ready to run these computations whenever needed. So who should those nodes be? And you should go in and find some of the trustworthy institutions in the society. And clearly there are some, like some industries are more trusted than others, so you could try to organize these entities and make them basically allow them to profit on selling trust in a system like this. You could also go to public institution. Maybe that's at least if you look at the governments. This is the United States, but I think this picture is pretty much the same in many other countries. But there are other studies that is actually showing that there is a lot of trust in some of the institutions. This is comparing the police, whether you trust the police, whether you trust other people. So there is a lot of trust out there. So you could organize, and if you have this sort of distributed cryptography, this is actually a tool to create these social institutions, put these trusted institutions, persons into networks, and create even more trust, and use that to realize some of these prospects in a data-driven economy. And I think that was actually my conclusion. So the conclusion is that okay, this has been used. I mean, there's an increasing opportunity to use MPC to solve a number of problems. And we would argue that there's a nice complementary match between the blockchain and the MPC technology. And that's what we're trying to utilize. So exciting prospect that we could actually realize this data-driven economy in a privacy-preserving manner. So this is not really new. Halvarian, 1995, he wrote in one of his papers who should be these institutions that is safeguarding these data that we just talked about in realizing such a data-driven economy. I think that was it. Thank you.
We have time for questions.
Hi, my question is why blockchain, and wouldn't something like a trillion personality solve the same trust issues without all the hype?
Excuse me, could you give me that again?
My question was why blockchain, and wouldn't something like a trillion personality solve the same trust issues without all the hype around the term blockchain?
Yeah, blockchain is one solution. So what we're trying to do is to utilize some of the things we think works well with blockchains. And combine that with what we think works well with MPC. We don't want to just go in and maybe just take the first random nodes in a public blockchain and have them running an MPC. So it's a different setting that we are focusing on. But I think that would require a lot more information about this, what we are building, and we would like to sort of postpone that a little more.
Okay, thank you.
Hi, you're claiming that you use the blockchain to perform MPC. I'm curious, having worked on blockchain tech now for some time, essentially, how are you actually using the blockchain to kind of ensure the correct computation here? Because it doesn't necessarily add any transparency unless you use certain techniques. So what techniques are you using to accomplish that transparency in comparison to like a cloud or just another trusted company's network that has physical security and stuff like that?
Yeah, so that's what we would like to present at a later stage. But
you're presenting it later?
Yeah, so that's what we are creating. We're creating this infrastructure now. So I'm just sort of laying out this new project in some weak terms.
Do you have a proof of concept up at all, or?
Yeah, so we have the first proof of concept of the basic network. So this is what we are creating. So the two applications that I've talked about, this tailor-made solution for the blockchain and MPC. That's one way of working with this. Separate entities who's actually running a business using this technology. Then we say, okay, that looks great. We want to actually make it easier for others to do the same, and we have some learned lessons from this combination, and that's what we're using to create this infrastructure that combine blockchain and MPC. And the more details about this. First of all, that's why I'm giving the talk. I will not be able to reveal anything. So I'm the economist, so and we will need some more time to get the basics in place. But we do have actually a first implementation, and yes.
Cool. Thank you. That's it. Thanks. Thank you.
Thank you again. Have a good meal. We reconvene at 2 p.m.